So up to now, we've really been dealing with something called restricted wave functions. They're called restricted because all of the electrons in the molecules are paired. They're restricted to be in the same orbitals as the corresponding alpha or beta electron. But of course, we're going to talk about a lot of common molecules like oxygen and other molecules that have unpaired electrons. And so we need to be able to treat these unpaired electrons. So just to think about oxygen, if we compare oxygen and nitrogen, so we've got an MO diagram for nitrogen on the left, diagram for oxygen on the right, well, we have 2 extra electrons for oxygen, and those go up here. These are both unpaired electrons in the pi orbital. And so the ground state of oxygen is a triplet. Another case where we really need to think about this is something like the methyl radical. So in the methyl radical, we have a lot of doubly occupied orbitals. So there'd be a doubly occupied orbital that's related to the 1s electron, or the 1s electrons on carbon, those core electrons on carbon. And we'd also have some doubly occupied electrons related to the CH bonds in the molecule. But then we're going to have one orbital that's a singly occupied. So we just have one electron in this particular 2p orbital. So let's think about how ROHF would represent this. So in a restricted open shell Hartree-Fock, we're going to end up having all spatial orbitals for the alpha and beta will be exactly the same. So it's the typical picture that we would have thought of from freshman chemistry. So we'd have our carbon 1s, which is doubly occupied. We'll have the different bonding orbitals for the CHs. Those are all occupied. And then we'll have this singly occupied carbon PZ. Now, on the other hand, an unrestricted Hartree-Fock, which is often called also a spin polarized calculation, this one can now allow, it basically breaks the restriction that the alpha and the beta electrons, the up and down spin electrons, have to be in the same orbital. It allows these orbitals to vary, so their energies can be different as well as their coefficients can be different. And so now we have alpha orbitals and beta orbitals. So we'll have, in this case, an upspin electron in the 1s alpha orbital and a downspin electron in the 1s beta. And so we can continue on. And again, these energies don't have to be the same, the coefficients don't have to be the same. It accounts for the fact that this alpha electron will interact differently with these other alpha electrons than it will with the beta electrons. Now, so far I've just been talking about ROHF and UHF as being restricted open shell Hartree-Fock and unrestricted Hartree-Fock. They're the same versions for DFT as well. Again, the same idea of either keeping the alpha and beta to be the same or allowing the alpha and beta orbitals to have different spatial orbitals, different coefficients, different energies. So everything I'm saying about Hartree-Fock, you can really apply to DFT as well. All right, so let's talk about advantages and disadvantages of these methods. So the big disadvantage of the UHF wave function is that it's not an eigenfunction of the S-squared operator. So the wave function that you end up getting out is not a true doublet or a triplet state. There's something called spin contamination from the higher spin states. And so when we are using UHF, we really want to make sure we look at this S-squared expectation value. So we'd expect it to be 0 for singlet. We'd want it to be 3/4 for a doublet. That comes from the fact that we'd have S times S plus 1, and S is equal to 1/2 for an electron. So we have 1/2 times 3/2, so 3/4, so 0.75. For a triplet, we'd have a value of 2, again, S times S plus 1, where S is equal to 1. Now, if something is very spin contaminated, that's a good suggestion that maybe these unrestricted wave functions, maybe that's not sufficient. Maybe we need to go to something that's maybe multi-reference or something else. So it can be a good hint that maybe a single reference wave function is not appropriate. There are some methods, I've just mentioned one here, which is called projected UHF. It attempts to account for projecting out some of the spin contamination. It's still not great, but people are working on developing better methods that will project out some of that spin contamination. All right, so anyhow, spin contamination is really the big disadvantage of UHF. ROHF, it's not a problem. By construction, all of the wave functions are eigenfunctions of the S-squared operator. Where ROHF has problems is that it cannot account for spin polarization. So it does not account for the fact that that extra alpha electron will actually affect the location of the other alpha electrons. And so ROHF cannot do that. So for example, in the methyl radical on the previous page, if we were to calculate some ESR spectra, we'd see a value of 0 for the hydrogens, but in reality, it should not be 0. Okay, just a point is that UHF can actually take a little bit longer to calculate because we do have different alpha and beta orbitals. The coefficients are different for alpha and beta. It does change a little bit the routines when we're solving the SCF equations. We've got a little bit more integrals, more equations to solve. But still, it's a factor of usually 3 to 4. And as just a final point, final takeaway message, I just want to leave you with the idea that open shell systems really are always going to require more thought and care than closed shell systems. There tend to be a lot more ways where that single electron can go. And one always has to think about ROHF versus UHF, which is better for your particular case. How much spin contamination do you have? These open shell systems might not be single reference the way a lot of closed shell systems might be. So you might have to think about moving to a multi-reference wave function, various things like that. So there's always a lot more thought that you should put into thinking about open shell systems.